Our sun feels enormous. It contains 99.8% of all the mass in our solar system. 1 million Earths could fit inside it. Its surface is hot enough to vaporize steel in seconds. And yet, in the grand scale of the universe, our sun is almost embarrassingly average. Because out there in the depths of space exist stars so large that if you placed one at the center of our solar system, it would swallow every planet out to Jupiter and keep going. Stars so luminous, they release more energy in 4 seconds than our sun produces in an entire year. Stars so massive, they tear themselves apart just by existing, hurling material into space at 3,000 kilometers per second. And in the southern constellation of Scutum, we believe we've found the largest one ever detected. This is the story of the universe's true giants and what they reveal about the ultimate limits of nature itself. To understand the largest stars, we first need to understand what a star actually is. A star is a battle, a continuous, violent struggle between two opposing forces. On one side, gravity, the crushing inward pull of the star's own mass, always trying to collapse it into a single point. On the other side, radiation pressure, the explosive outward push of energy produced by nuclear fusion at the star's core. When these two forces balance, we call the star stable. Astronomers give this state a precise name: hydrostatic equilibrium. Almost every star you can see in the night sky is in this state right now, including our sun, which has maintained this balance for 4.5 billion years and will continue for another 5 billion. But the nature of this balance depends entirely on mass. The more massive a star is, the harder gravity crushes its core. Greater pressure means faster fusion. Faster fusion means more energy. More energy means the star swells outward. This is why the most massive stars are also the largest and the brightest. It's a chain reaction written into the laws of physics. But there's a limit. The more energy a star produces, the harder it pushes against its own outer layers. At a certain point, the radiation becomes so powerful that it overcomes gravity entirely, and the star begins to destroy itself from the inside out. This limit, the point where a star becomes too massive to hold itself together, is called the Eddington limit, and it places a hard ceiling on how massive a star can grow through normal means. That ceiling is roughly 150 times the mass of our sun. Go beyond it, and a star becomes so unstable, it tears itself apart in violent eruptions, or blows itself to pieces entirely in a matter of millions of years. And yet, the universe has found ways to cheat. Most stars spend the majority of their lives on what astronomers call the main sequence, a stable phase of hydrogen fusion that can last billions of years. Our sun is a main sequence star. So is Sirius, the brightest star in the night sky. So are the Alpha Centauri stars, our nearest neighbors. But at the far end of the main sequence live a very different kind of star. Take Bellatrix, the left shoulder of Orion. It burns at 22,000 degrees Kelvin, nearly 4 times hotter than the sun, 8 times more massive, 200 times larger in volume. And Bellatrix isn't even close to the top. At the extreme end of the main sequence lies a class of star called Wolf-Rayet stars. These are the most massive, most luminous, and most violent stars we know of, still burning hydrogen in their cores, but doing so in a way that defies ordinary comprehension. The most extreme example ever found is R13601, located in a star-forming region called the Tarantula Nebula, 160,000 light-years away in the Large Magellanic Cloud. R13601 is estimated to be 265 times the mass of our sun. How it exceeded the 150 solar mass limit is still debated. The leading theory is that it formed from the merger of two already massive stars colliding and combining early in their lives. Its luminosity is staggering. It releases as much energy in 4 seconds as our sun emits in an entire year. In total, it shines approximately 8 million times brighter. But here's the strange thing. R13601 is not the largest star, not even close, because sheer mass and sheer size are very different things. To find the truly largest stars in the universe, you have to look not at young giants, but at old ones, stars that are approaching the end of their lives, stars that have exhausted the hydrogen in their cores and are now entering a final, desperate phase of expansion. Here is what happens. When a star burns through the hydrogen at its core, fusion stops. Without the energy of fusion pushing outward, gravity begins to win. The core starts to collapse inward. This collapse generates enormous heat and pressure. Eventually, the core becomes hot enough to fuse helium instead of hydrogen. A new energy source ignites. But this heat also radiates outward into the star's outer layers. The hydrogen in those outer shells, previously too cool to fuse, suddenly reaches the temperatures it needs. A new wave of fusion begins, not in the core, but in a shell surrounding it. The energy released is enormous, far more than the star was producing before. And with all that extra energy pushing outward, the star expands, dramatically, catastrophically, to sizes that defy intuition. This is the red giant phase. And for smaller stars like our Sun, it is the final act of their lives. In about 5 billion years, our Sun will expand to a diameter of 300 million kilometers, large enough to swallow Mercury, Venus, and possibly Earth. But for the most massive stars, the red giant phase leads somewhere even more extreme. It leads to something called a red supergiant, and that is where the true giants of the universe live. A red supergiant is what happens when a star 8 or more times the mass of the Sun reaches the end of its life and begins to expand. These are not merely large stars. They are the largest physical objects in the observable universe that are not structures, individual, single stars of incomprehensible scale. You likely know the most famous example, Betelgeuse, the left shoulder of Orion, the same constellation that contains Bellatrix. Betelgeuse is a red supergiant approximately 700 times the diameter of our Sun. If you replaced our Sun with Betelgeuse, its surface would extend beyond the orbit of Jupiter. Every inner planet, Mercury, Venus, Earth, Mars, would be completely engulfed. Jupiter itself might not escape. Betelgeuse is also one of the closest red supergiants to Earth, sitting at roughly 700 light-years away, which is why astronomers watch it so carefully. In late 2019 and early 2020, Betelgeuse dramatically dimmed, what became known as the Great Dimming, triggering widespread speculation that it was about to explode as a supernova. It wasn't. Not yet. But it will, within the next 100,000 years. When it does, it will briefly shine bright enough to cast shadows at night on Earth. But even Betelgeuse, vast as it is not the largest star we have found. In the constellation Scutum, a small faint constellation in the southern Milky Way, sits an object that has repeatedly claimed the title of the largest known star. Its name is UY Scuti. UY Scuti is a red supergiant located approximately 5,000 to 9,000 light-years from Earth. It is the kind of object that makes scale feel completely meaningless. Its radius is estimated at approximately 1,700 times that of our Sun. If you replaced our Sun with UY Scuti, its surface would extend past the orbit of Jupiter, possibly past Saturn. 5 billion suns could fit inside its volume. And yet, UY Scuti is not especially massive. It is roughly 7 to 10 times the mass of our Sun, far less massive than R13601. What it lacks in mass, it has made up for in sheer physical size through the expansion of its outer layers. It is also cool by stellar standards. Its surface temperature is only about 3,400 Kelvin, compared to the Sun's 5,778 Kelvin, which is why it glows that deep, somber red. Because of its distance and low surface brightness, UY Scuti is actually invisible to the naked eye. You need binoculars or a small telescope to see it at all, which feels almost absurd for the potentially largest star in the galaxy. UY Scuti is also nearing the end of its life. It is already 10 to 20 million years old. Within a few million more years, it will exhaust its remaining fuel, shed its outer layers, and collapse, triggering one of the most violent explosions in the universe, a supernova. Before a star like UY Scuti reaches that explosive end, it may pass through one final transformation. As it continues to exhaust its fuel and shed mass, its outer layers thin out, its core grows hotter. The character of the star begins to shift. This is the hypergiant phase, and it produces some of the most extreme objects in the known universe. Yellow hypergiants are among the rarest and most unstable stars we know of. They are in a state of violent transition, blowing off entire Jupiter masses of material in single explosive events, surrounding themselves in vast shells of ejected gas and dust. These ejected materials are not simply waste. They are the ingredients of future solar systems: carbon, oxygen, nitrogen, iron. All the heavy elements forged inside the star over millions of years, now scattered into the interstellar medium, where they will mix with other clouds and eventually condense into new stars and new planets. The material now inside your body was forged in stars like these: the iron in your blood, the oxygen in every breath, the carbon that forms your DNA. All of it came from a star that died. And among the candidates for the largest star beyond our own galaxy, one object stands out: WOHG 64, a red supergiant in the Large Magellanic Cloud, 160,000 light-years away. It is the only star outside the Milky Way that we have ever directly imaged. Recent observations suggest it may have already transitioned into the hypergiant phase, shrouding itself in a thick shell of ejected material. It may be comparable in size to UY Scuti, or potentially even larger. At that distance, measurement is extraordinarily difficult. We simply don't know yet. Every red supergiant, every giant star nearing the end of its life, is approaching a fundamental boundary written into the laws of physics. It's called the Hayashi limit, named after Japanese astrophysicist Chushiro Hayashi. This limit describes the maximum size a star of a given mass can reach. Beyond it, the physics of convection, the churning movement of hot gas inside the star, changes character. Instead of transporting heat outward efficiently, convection begins to work against the star's structure. Gravity starts to win again. The star can no longer expand. On the Hertzsprung-Russell diagram, the fundamental chart that plots stellar brightness against temperature, the Hayashi limit appears as a vertical boundary on the right side. No stable star can exist to the right of this line. UY Scuti is already very close to this limit. Any star that approaches or crosses it becomes violently unstable, pulsating, shedding mass, oscillating between expansion and contraction. This is why astronomers believe there is likely a hard ceiling on stellar size in our universe, something in the range of 1,500 to 2,000 solar radii, with UY Scuti already pushing against it. But there are things we don't know. Could there be types of giant stars in other galaxies that we haven't yet discovered? Could conditions in the very early universe, when gas clouds were more abundant and metal content was lower, have allowed stars even larger than any we see today? The honest answer is, we don't know. And our technology is only now beginning to reach the point where we might find out. The James Webb Space Telescope, designed to see the earliest light of the universe, is now beginning to reveal something unexpected about stars. In the most distant galaxies Webb has imaged, the first generation of stars, called population 3 stars, are theorized to have been very different from the stars we see today. The early universe contained almost no heavy elements, only hydrogen, helium, and trace amounts of lithium, the direct products of the Big Bang. Without heavy elements, gas clouds cooled more slowly. Without efficient cooling, they couldn't fragment into small clumps. Instead, they collapsed into massive objects, some theorized to be thousands of times the mass of our Sun. If these stars existed, and Webb is now searching for any surviving signature of them, they would have been incomprehensibly luminous. They would have burned through their fuel in mere millions of years. And when they exploded, they would have seeded the universe with the very first heavy elements, the starting ingredients for every star, planet, and living thing that came after. We have never directly observed a population 3 star. They are too distant and their light too ancient. But James Webb has already found objects in the very early universe whose signatures hint at stellar populations with unusual properties. The story of the universe's largest and most ancient stars is still being written, and the telescope that is writing it is pointing at the sky right now. The largest stars in the universe are not long-lived triumphs of nature. They are brief, violent, catastrophic phenomena, objects so massive and so unstable that they tear themselves apart in geological eye blinks. UY Scuti, the largest we have found so far, will be gone within a few million years. Betelgeuse, its smaller but closer cousin, could explode within the next 100,000. R136A1 has already lost enormous fractions of its original mass to violent stellar winds. These giants do not endure. They burn, they erupt, they collapse, they scatter. And in that scattering, they do something extraordinary. They build the universe. Every heavy element, heavier than iron in your body, was forged in the death of a massive star. Every atom of carbon, nitrogen, oxygen, every building block of the biology that makes you alive, passed through the heart of a star before it reached you. The universe's largest stars are violent, short-lived, and self-destructive. But they are also, in the most literal sense, the reason anything else exists at all. Thanks for watching.